problem 1 here, we have a crate, and which slides from a certain location. We talked about this before the test. So you have an acceleration A, and acceleration A is here, but initial velocity is here, right? And then, so you consider displacement. So the first, it will start moving from here, and it will momentarily stop at this location. At this location, you can call that some v star equals 0, and then it will continue moving all the way to some final point here, right? So now, suppose the final velocity is given, v final is known, right? And v initial is known as well, and we want the total distance. So I talked about that problem in the homework as a homework question, and that homework question has 4 parts, right? So I suggest that you review all the whole parts, 4 parts before the test. That's what I suggested in class, right? And so this question here, they ask about total distance. The total distance means you need to consider here. So this is the first displacement. At first displacement will go from here to here. Let's call that delta x1. And delta x2 is this one. Okay? So this is delta x2. And so total distance, we call that d will be equal to absolute value of delta x1 plus absolute value of delta x2. Right? So first you need to get delta x1. So use one of the kinematic equations. Treat this as a final. This is an initial. So you have that 0 square, right? So delta x1 you can obtain from the following equation. You can say that that v star, okay, v star is actually 0 square equals v initial square, then plus 2 times the acceleration times delta x1, right? And then here you have 0, okay, 0 meter per second square, and the v initial is negative 5.1 meter per second. You square it, then plus 2 times the acceleration. Acceleration is known, right? What's acceleration? Acceleration is 3.15 meter per second square, and times the displacement delta x1. And you solve for delta x1, right? You solve for delta, so delta x1 you can solve it, and then you will obtain delta x1 here, right? Now, for the second displacement is from here to here, right? From here to here. So therefore, you need to treat this as an initial. And the very final, you treat it as final here. So then you have the v final square equals the v, now the v initial become that v star, which is 0, right? Then plus 2 times a times delta x2, right? Okay, and you need to figure out delta x2. So how would you figure out delta x2 here? So you can consider v final. V final is given, right? So it's 10.2 meter per second. You square it, then equals the v initial, which is 0. You square it plus 2 times the acceleration. Acceleration is also given 3.15 meter per second squared. Then multiply by your delta x2 here. And potentially this delta x1 you get will be negative, right? Because delta x1, but delta x2 will be positive. So we talked about this in class already, right? So then this delta x1, if you want the expression, that would be you'll be negative. So that will be this thing. It will be like a 5.1 square, right? But it's actually negative 5.1 square, but the negative sign will be gone. But now you have additional negative sign as well outside of the square, and then divide by 2 times like a 3.15, right? And you can carry out numerical value here. And delta x2 here will be a positive quantity. So delta x2 will be 10.2. You square it and divide by 2 times 2 times 3.15, right? This thing, and you obtain delta x2. But when you do the sum, as I have said, you do the sum. You take the absolute value first, and then do the sum, right? Once you carry out this and this, then you take the absolute value of each and do the sum. You get the total distance, right? Total distance. So pay attention. In that homework problem, there are A, B, C, and D, right? And this is roughly to part D of that homework problem there. So, okay. So I drew your attention to that problem. I mean, when I gave the lecture about this topic there. So now the next, the problem 2. Okay, problem 2. So problem 2, we are considering about this question here. So it's a chasing problem. Okay? So Brandon and his opponent, and eventually, but of course, as I have said on each test, I can change the questions, right? So I change, so and like this question, I change the final question there. So what is the speed of Brandon at that point, right? So basically, this question we also cover in class as well. About the procedure of solving such a problem here. So the problem number 2 is a chasing problem like this. So Brandon here and his opponent, right? So let's call Brandon person A and his opponent person B, right? So we talked about this in class already. So suppose so this was a starting point, x equals 0, okay? So when they first met, then that's x equals 0. And then afterwards, Brandon moved with a constant speed, and then for a certain time, we call that VBT star, right? And after that, we assume that the common clock start ticking. So this is the t equals 0 for his opponent, and his opponent was at this location when t equals 0, right? And then Brandon, person A, was at this location when t equals 0. Then clock, okay? Suppose they have a common clock or common watch. That clock start ticking at this moment, but Brandon was at this location and his opponent was at this location. And then overall distance, we can call that XA, right? And for Brandon and for his opponent, this overall distance, we can call that XB, right? And in class, we say that in the end, Brandon will catch his opponent, right? And we can say the final time to be, say, some final t, okay? Final t final. For this problem here, still you need to solve for t first. Okay, solve for t first, and then once you solve for t, you'll be able to know so let's say that final time is t. Okay, final time is t for both, and we can consider xa equals xb. Okay, the total displacement for the two. Okay, this one. Okay, and this overall displacement. But be careful about his opponent here. His opponent, his watch, his opponent's watch start from here. So that means before his watch starts, his opponent has already traveled for this distance here. So be careful about this. So then Brandon, that displacement is 1/2 AA, let's call it acceleration A sub A, okay? T squared and equals the XB equals the VB times T, because this trip is like a VB times T. VB times T. So VB times T plus VB times T star, something like this, right? So you have such an equation and solve for time. And T star is actually a constant, right? So that means T star is given, let's say T star is given by a problem which is 1.8 seconds, right? So T star is that 1.8 seconds. And that VB is uniform. We know that VB is given 4 meters per second. And acceleration AA is also given. AA is 0.48 meter per second squared, right? And then you substitute everything into here, so then you have 1/2 this thing, 0.48, okay? Meter per second squared times the unknown t squared equals VB, which is 4 meters per second times t, then plus VB times t star, so that's 4 times 1.8. Okay? Yeah, and then that's the equation we have, and you can solve for t, right? You can solve for t, and here, of course, most of you, I believe, have solved this problem. Here, I just want to draw attention to the last step. Right? You solve for t. So this is something we talk about in class. So 1/2 this thing, right? So 1/2. So you have 1/2 times 0.48 times t squared, then minus 40, then minus 4 times 1.8. Okay? 4 times 1.8 equals 0, right? And then what you do is solve for t first. So t will be equal to 2 times a. Okay, so that's 0.48, Then here you have negative b, so that's 4, plus or minus b squared, so that's negative 4 squared. Okay? Negative 4 squared is just 4 squared, that's 16. Then minus 4ac. Okay, so minus 4, okay, 4 times, let's compute 4ac here. Okay, 4ac equals 4 times 1/2 times 0.4a, then times c. C is this one. Okay, so C is actually negative 4, so okay, times negative 4 and then 1.8, right? So that's why. So this one you get a factor of 2, and this will become plus. So you can consider this as 2 times 4 is 8. So okay, so you can consider that as 2. So a times 0.4a. Then times 1.8, something like this. Right? But now it will become plus, right? So here I just combine some vectors. So this is 2, and this is, so 2 times 4 is 8. So in your calculator, you input this and drop the negative solution because time is always positive. Then you can get that time, right? So once you get the time, then how would you obtain the speed of Brayton? Speed of Brayton will just be obtained by that kinematic equation, right? The speed of Brayton, since you can also compute that distance that Brayton traveled, but the speed of Brayton, you can use this V final equals V initial plus A times time, right? So then V initial, Brayton starts on 0, okay? So V initial is 0, and this A is, of course, the acceleration of Brayton. That's the A sub A, okay? So that's the acceleration of Brayton, which is 0.4A, and then meter per second squared, then times the time that you obtain from here, okay? Times the time you obtain from here, then that will be the final speed or final velocity of Brayton, right? So that's the second part of the question. Now let's look at the problem 2, okay? And problem 6, let's talk about problems. Problem 6 we have covered in class, okay? If you attended lecture, you know that this is something, I gave you a hint in class that I will give such a question here. And such a question here, so just need to be careful about, I gave a hint, okay? In a lecture before the exam. So this question here is actually not difficult if you know what we are asking for. So there's A, B, and C, right? And so A, B, and C, 3 locations, A, B, and C. And we wonder what's from A to C, okay? From location A to location C, we wonder what's the average speed for the person. Average speed, we know that it's the total distance over the total time required, right? Total distance travel. So here, we know that, here we have L, right? So this distance L, this is 4L. So the total distance will be L plus 4L, right? Then the time required, you consider, because the speeds are actually different, right? The first speed is given, it's called V1, and second speed is also given, called V2, right? So the speeds are different. So time would be equal, here you need to consider distance for the first segment of travel. The time required will be L over V1, right? And the second distance of travel, the time required will be 4L over V2, right? So then you add up the time, you get something like this. Now you can substitute in the numbers. So here you have 5L, okay? But pay attention, you can extract the common L here. So here you have 5L, 5 times L, right? But here what you have is you can extract the common L, and here you have 1 divided by 1.45 meter per second square, right? So meter per second, then plus 4 divided by 9.5 meter per second, right? Something like this. And then you will see that L got canceled out, right? L got canceled with each other. So that's the rest you can compute, right? The rest you can compute, then you will be able to get the correct answer here. Okay, so of course this L, we can assume that it's some unit, can be in terms of meters here, right? But anyway, but L got canceled out, so then you will be able to get the correct answer in terms of, so this final speed, of course, will be in terms of meter per second, right? Because if you look at the unit, it will become a meter per second in the end. So that's it. Okay, so that's this problem here. Average speed from A to C, right? And now let's look at this problem here. This problem, what do we want to obtain? You need to obtain the speed of the ball when it just crosses the fence, right? So pay attention, this point here is not the maximum height, okay? So that's just some particular point. If you play football, you know that 3 meters is not the maximum height, right? So do not use, as I say, you don't, so pay attention, right? So don't use the equation for maximum height, because that 3 meters is not maximum height. So you actually need to know the time first, right? So the method is actually not unique, actually, but there's no, there are a couple of methods which you can solve this problem here. But here, let's consider how we solve this problem here. So problem 6, you consider this ball which is launched with a certain initial velocity, and suppose it will pass through this point here. This point, we can call that point P, for example. Okay, point P is not the maximum height, okay? Not the maximum height. And we want to consider, but we know the height, but so we want, and we can call that height H, for example. Right? So now let's try to consider how we obtain the speed at that location. By speed, we mean the following. Let's say the velocity is called Vp, okay, for example. And if you decompose that Vp onto the two components, you can see that, so this is Vp, the x component of Vp, right? And the y component of Vp, let's say Vp comma x and Vp comma y, okay? And Vp comma y, two components. But what is Vp comma x? Let's consider the initial, right? The initial point here. Here you have V naught, so here you have V naught cosine theta naught, and here you have V naught sine theta naught, right? And we know that this V naught cosine theta naught is unchanged, so that means Vp comma x. So okay, problem 6. Vp comma x will just be equal to V naught cosine theta naught. Okay? That component is unchanged. It will maintain this component since there is no acceleration of acceleration, but the y component will change, right? So how would that change according to? It will change according to an equation we told you before. Look like Vpy, okay? Vpy should be equal to that initial y component of velocity, which is V naught sine theta naught, then minus g, then minus the time, okay? And that time we can call that either TP, we call that T star or TP, right? So or just call it T, it's fine, right? Just call it T or TP. Let's call it T or something. TP. Let's call it TP, right? So, but here still, we do not know this, right? But once you know both components, how would you get the speed? The speed, like Vp, the speed means the magnitude of velocity, would just be use Pythagorean theorem, right? Vp comma x squared plus Vp comma y squared, right? So that's how you get the. So that's what we meant by speed. Speed means magnitude of velocity, right? That's the speed at this location here. But now the question is, how do you get the TP, right? So let's look at what information we know. We know this height here, right? Know this height here. So you can use that y equation in the y direction. So use the equation in the y direction. You have y final. Okay, so let's say yp minus y naught. Okay, and this equation we can consider this as V naught sine theta naught times T, okay, or T or TP, right? TP, then minus 1/2 G TP squared, right? But this what is this thing? This thing is just the H, right? YP minus Y naught is just the H. So for this question here, you need to solve for TP, right? So now let's just substitute in the number. What is H? Well, H is 3 meters, right? So 3 equals V naught is 12 times sine theta naught, sine 55 degrees, and times the unknown TP minus 1/2 times 9.8 times TP squared, right? And so then now let's write down the equation for TP. So shift this term to here. So then you have 1/2 times 9.8 and times TP squared, and then minus 12 sine 55 degrees, and times TP, then plus 3, right? And equals 0. Let's see if we make any mistake. So here we have a positive 3, that's right. And here you have the things written down correctly, and then you can solve for TP, right? So TP will be equal to 2a, but 2a will just give you 9.8 here, right? And then negative b, so sorry, negative b is the 12 sine 55 degree. Then you can say plus or minus like a b squared minus 4ac, right? Yeah, I don't have enough space here. Let's do it here. So b squared minus 4ac will be equal to b is, so let's call this a, okay? So I call this a, call this part I call it b, right? And this thing I call it c, right? So b squared minus 4ac is the 12 sine 55 degrees, right? It's a negative term, but you square it, right? Then minus 4 times a is 1/2 9.8, and then times c, which is 3, right? So then here you get a factor of 2 here. But anyway, so then you substitute this part into there, you get the time, right? You get the time. And of course, here you have plus or minus, so keep the positive answer. Then once you have the positive time, you substitute this into here, then you have the two components of velocity, then you'll be able to get the speed in this way, right? Okay, so that's it. So this is actually, sorry, this is problem 9. Okay, so problem 6 was the earlier one. So this one is problem 9 here, right? So that's it. Okay, problem 9 of the question. So now, so the rest you can figure out by yourself. I mean the rest questions on the test here. Right? Okay, so now let's move on to the following. So okay. So let me say again. So this thing you input that into the square root here. So I separate the writings on the two sides of the whiteboard. But the b squared minus 4ac you put it here, right? The thing I call it b squared. The b squared minus 4ac, you put it into here. Right? You substitute that into here. So now let's move on to chapter 5. So I think you have already received the slides. I mean, on Blackboard, there's a new folder. On Blackboard, you see a new folder, and the slides of chapter 5 have been put in that new folder there. Right? So now let's consider here. There are several files I put in the new folder. So let's start with the chapter 5. All the instructor here, we will start with the main point is actually in section 5.4. Okay? So we start from 5.4 here. 5.4 here is called Newton's second law. So you may wonder why didn't I talk about Newton's first law first? Because Newton's second law is more computational, and first law is actually more conceptual, but first law is actually conceptually difficult, a bit difficult to understand conceptually. So we start with computation, and then at some point we will come back to the first law. Okay, first law is in the previous section. The previous few sections you will learn about the first law, but we start with section 4, which is most important section. So suppose now you are going to move an object. Okay, say I have an object here. And suppose I would like to exert a force so that it will move. Okay, it will move. And then let's assume that that object will move with a constant acceleration. Okay, we try to exert a force so that it will move with a constant acceleration. Then what we can do is, you're in a certain lab this semester, probably in the next few weeks, you are going to see a lab about this, about Newton's second law. We're going to verify this. So the consideration is, if you try to fix the acceleration. I'm sorry. If you are going to say, first, if you will fix the mass, then you will see that your force will be proportional to your acceleration. And if you try to fix the force, you will see that your mass will be inversely proportional to acceleration. Okay? So you are going to see in the lab, and in a certain week, you are going to see this kind of consideration here. Let me say that again. Okay? So we will see that there's a relation among force, mass, and acceleration. So that's relevant to chapter 5 of the book, and mainly in section 4. Okay? Mainly in section 4 here. So in chapter 5 of the book, what we consider is as follows. And this, we consider we are trying to move an object with a certain applied force. We can call it F applied or just F. Force is a vector. Once force is applied on that object, this object will undergo a certain acceleration. We call that acceleration A. And we have studied acceleration more extensively in chapter 2, right? And also chapter 4, we also study acceleration as well. But now we are in chapter 5. We need to consider what's the relation in between acceleration and the force. Okay? So actually, if you fix the mass, okay? So if you fix the mass of the object, then people will see that the acceleration magnitude will be proportional to the force magnitude if mass, okay, is constant. If you fix the mass, you will see such a relation here. So that's why for convenience, people just try to define certain constant so that they can specify the relation in between force and acceleration. Okay? So since when mass is a constant, then acceleration will be linearly proportional to force. So then people start to define it this way. They just define F to be mass times acceleration. Right? So they define it in this way. But this is how we define a force actually. So that means you can consider force to be just equal to the mass times the acceleration. But people may ask, why isn't there any other constants in front of mass? So this part is artificial. That means we try to define our units so that the unit for mass times the unit for acceleration will just be the unit for force, right? So that we don't need to insert any other constants. So now let's check the SI units, okay? SI units. So the SI unit for mass, we know that it's in kilograms, okay? Not for grams, it's kilograms is the SI unit for mass. How about the SI unit for acceleration? SI unit for acceleration, it's actually meter per second square, right? So now, for our convenience, we want this product to be the unit for force because we don't want any other constant in front of mass. Okay? So that's for our own convenience. So then what we should consider is define the SI unit for force. Right? So this is experimental result. Okay? In a lab, you will be able to verify this. And this result, from this experimental result, if you try to define the SI unit for your force, then what you do is as follows. The SI unit for force should be equal to the SI unit for mass, right? Times the SI unit for acceleration. That's our consideration here. Okay? Of course, force is a vector, but here we just consider the magnitude of it. And then this will be, of course, kilogram times meter per second square. Now we want to call this a new unit. Okay? So the SI unit for this thing, we call it newtons, capital N, and it's pronounced as N-E-W-T-O-N. Okay? Newton. So that's the SI unit for force. So now, from now on, on most occasions, we will not use pounds as force. We call the SI unit for force to be newtons, right? So 1 Newton equals 1 kilogram of mass multiplied by 1 meter per second square of acceleration. So that's the SI unit for Newton. So again, we don't use pound for most of the occasions from now on. Okay? So you can read the statement about Newton's second law, but I think our point is about computation. Okay? So you can, if you are interested in, you can read the textbook about how they construct such a relation. But for us, okay, you can just memorize the relation. Okay? But then when we come back to Newton's first law, we're going to consider more deeply about what's the meaning of such a relation here. But here we just stay with the expression, and we have F equals ma. And that F actually means net force. So very often, people can say that our textbook, they will use the sum, okay, the capital sigma. That means the summation. So other books, they may call this F net. Okay? So when you see either F net means net force. You can either call it F net or the sum of F. Okay? That capital capital sigma means the sum. Okay? So that means when you see such a notation in the textbook, like they call it sigma, but that's actually sum. So that means F net is defined as sum over F. But that was just a shorthand notation. Actually, they should write down, say, sum over Fj and j from 1 to n, for example. Okay? So that multiple forces, that actually equals F1 plus F2 plus F3 plus F4 and so on. Okay? When you see such a notation, that like sum over F, that means actually means the net force. That some other book, they will call it F net. Okay? Just this simple. But our book, they will simplify this notation to be just the sum and then F. Okay? They omit the J subscript, then they remove the index J from the sum. But actually this moves, so this means sum over the forces. Okay? Sum over all the forces exerted on that same object here. Okay? When you see such a notation, that F net, or either F net or this sum over F, okay, so it's actually, so this is a Greek letter sigma, right? But it's actually called a sum in math, right? It's a sum over the forces here. Now let's move on, okay? So SI unit, we have to talk about this. There are some details here, but there are two units for force. One is called Newton, and of course, the other is called a pound, okay? Pound. But pound, we don't need to worry too much about it. You just need to know that pound force is a unit for force in daily life. But Newton here is the SI unit. Most likely, we'll use SI units for the test, okay? And 1 Newton roughly equals 1/4 pounds. 1 Newton approximately equal to 1/4 pounds. That's the comparison. But now, from now on, we hope to stay with SI unit, okay? Because we don't want to do unit conversion like that. So basically, we try to stay with SI unit. But you still need to know pounds. I mean, but just for, most likely, we will use newtons as units for forces from now on. Right? So now we'll move on to other things as well. But now what we are going to consider is as follows. So there's an example in the textbook, so-called example 5.1. But this example here, today I don't plan to cover this in detail. But we'll come back to this example another time. This example means the following. There are two forces acted upon a park. Right? And this park, we are going to consider what's the net force exerted on the park. And then, secondly, we need to determine the acceleration. Okay? What's the magnitude and acceleration of the park? So what we consider here is as follows. In such a problem, we need to pay attention to the fact that there are two forces, right? F1 and F2. So my recommendation is you use the parallelogram method to determine the net force first, right? So this is example 5.1. Example 5.1. In this example here, you are going to consider two forces, right? So say F1 and F2. But there's a coordinate system as well. But the first thing we suggest you is use the parallelogram method to determine the qualitatively where is the net force, right? So net force will be here. Okay, and this example actually is in section 5.4 of the book. Section 5.4 of the book, example 5.1 here. So now, once you have done this, this is something relevant to the test. I mean, the first exam, right? First exam, you have the skill. Because this thing was actually relevant to chapter 3 as well. Okay? So now you have the skill about the force to get the net force, which is here. Now you can apply F net equals ma, right? So how would you obtain your acceleration? Just the net force divided by m. So your acceleration should be written as 1 over the mass times your net force. So remember, your net force has two components, right? So your acceleration should have two components as well. So your acceleration should be something like this. Let me show you. Acceleration on the diagram should look like this one. Okay? So if you want to draw your acceleration on the same diagram as in the force diagram, but normally we don't do that. Normally we drew acceleration somewhere else. But if you want to put it together with force, then it will look like this. So that means you rescale your force vector so that it will become, you will get your acceleration vector like this, right? Rescale it. Rescale it means multiply the force by some scalar constant, and then you will get acceleration, right? So now you can finish your computation. So this question is straightforward, but the concept is also not difficult. First, get the net force, right? Get the net force as a vector. You know the two components of net force. Now you can divide two components by a factor of m, then you will get acceleration, right? So then acceleration will be equal to this, right? Will be equal to the x component of a force divided by m times I hat plus the y component of force divided by the mass times j hat, like this, right? So this will be your two components of acceleration. Of course, you should carry out the numbers, right? Because all the numerical values are given, right? So you should carry out the numbers. And once you carry out the numbers, you know the two components of your acceleration. Okay, so this component will be your ax. Okay, so this component will be your a sub x. And this component will be your a sub y here, right? And you carry out the numerical values, you will see the acceleration in terms of meter per second, the two components, and then you can obtain the magnitude and direction, right? But in this question, it's quite simple because acceleration is into the first quadrant, so when you decompose it, when you decompose your acceleration, it will look like ax will be positive. And ay will also be positive, like this, right? So then you will be able to get the magnitude of your acceleration by the Pythagorean theorem. So magnitude of your acceleration will just be equal to square root of ax squared plus ay squared, right? And once you get the magnitude of acceleration, you can also get the angle. Angle will be this angle here. Okay? The same angle will be used for the force, both the force and the acceleration. They will have the same angle. Okay? They will have the same angle. So then once you have the both components of acceleration, you can say that tangent theta equals ay over ax. Right? The y component of acceleration over the x component of acceleration equals tangent of the angle. And now you will be able to obtain that angle, right? Because then you can compute arctangent. So arctangent of ay over ax, which will give you, in this case, since the vector just points into the first quadrant, this will just give you the angle theta here. Okay? So then you obtain the angle as well as the magnitude. So as I've said, this question concept is straightforward, but just the calculation is a bit tedious here. So we don't talk about the calculation right now today, right? But if you are interested in, you can look through the solution here. Okay? I posted slides already. Okay? You can go to the Blackboard, and there's a new folder there called the lecture materials from today to exam 2. So you will see the slides here. Okay? But anyway, so that part, the detail, you follow the textbook. Okay? You follow the textbook, or you can read my slides as well. Now let's move on to section 5.5 here. Section 5.5 here, we are going to consider what we mean by gravitational force. Gravitational force means the following. We have some equations there. In the textbook, you will see some equations, but I don't recommend you to follow that notation. So I don't want to display those things. That notation may not be very good. Okay, so these slides here, although it's from the textbook, I recommend you I will show you a different notation. Okay, that notation is not entirely good. So now let's look at this thing here. Let's look at the title here. Here we have a ball here. We have a ball here, and we are going to consider what is the relation between force and acceleration. So we have considered this thing, free fall, right? When you throw this ball vertically upward, you will experience a force, and that force, we know that should be downward, right? It should be down because we know that acceleration is down. So now since we are familiar with the relation between force and acceleration, let's consider the following. This force will generate, say, a constant acceleration for the motion, right? So you can see that when that force, once it leaves my hand no longer touches the ball, so that ball will be only subjected to force of gravity, right? Force of gravity. So force of gravity, we know that should be down. So since we know that force of gravity should be down, then we will be able to consider the following. Consider one relation. We know F equals ma. But now since we are interested in the force of gravity, so we can make some changes to F equals ma so that we are interested, we can discuss about force of gravity. Right? So section 5.5, the title is like this. So now I recommend using the following equations. F, we call it F sub g. This is called force of gravity. Should be equal to, now let's consider what kind of relation we want to use. Let's try to use this relation. Force of gravity equals the mass here, the mass, right? And then times the y component of acceleration, that ay is the ay that we use in my lectures, times j hat, right? Because it's vertical and you have a negative ay. And now what is ay? Very often I say that ay equals negative g. Okay? I recommend using this notation. So therefore, when you substitute negative g into here, you get a negative mg times j hat. Right? So just consider this relation here. This one. Okay? So you can remember this relation. That's why I recommend, because different books, they may use different notations. But you remember ay equals negative g. So ay is the negative acceleration, right? Because we always define positive y to be up. Positive y-axis is up, right? But your ay should always be negative. So your ay is here. Ay is negative g. And what is g? G is 9.8, right? So that's why this will be, ay will be equal to negative 9.8 meter per second squared. But g is positive. You know that, right? So that's the notation. So don't get confused by the notation. Positive y is up. Okay? So that's why ay should be negative. So ay is negative 9.8 meter per second squared. So that's why always consider ay as negative g. Right? But g itself is positive. Right? G itself is positive. So I think you are familiar with this. But ay is negative, but g is positive. G equals positive 9.8, right? Meter per second squared. So that's what we have here, right? So, but the notation in the textbook, I mean, you can read it, but just don't get confused. Okay? G itself is positive, but we always consider ay as a negative quantity. So that's our consideration here. So then what about weight? In the textbook, you will see a terminology called weight. And weight is defined as follows. So again, the notation in the textbook, I don't recommend that, especially the second last equation. That one, I don't recommend using that. That one can cause some confusion. Okay? So that's why I don't want to use that one. But now we have finished this section. This section is quite short. And very soon we'll move on to the next section. But, I mean, in the next lecture. But here I just want to draw your attention. What is weight? If you heard of a terminology called weight, let's call it W, equals the absolute value of the force vector. Okay? So that means since it's equal to the absolute value of the force vector, you can consider this as the absolute value of the negative mg, and that would just be equal to mg. Okay? So weight is a scalar actually. Okay? It would just be equal to the mass of the object times the free fall acceleration g. Right? So that means weight, when you ask about weight of the object, that weight should be quantified by newtons as well. So SI unit for weight, okay? SI unit for weight is also newtons, right? Because SI unit for the force of gravity is in newtons, but SI unit for mass is in kilograms. So that's the basic difference between weight and mass. Although in daily life experience, sometimes we use those two terms interchangeably, but in physics, we need to be careful. Weight is a force, okay? It's a magnitude of a force, but mass is different, okay? It's different from weight. Their SI units are different. But in daily life, weight, we can also use pound to measure, right? For non-SI unit, we can also use pound force to measure weight, but the mass, we use SI unit kilograms, okay? But the SI unit for weight is newtons. So that's the conclusion here. And next lecture, we'll move on to Newton's third law. And I also recommend you to read the file first. There's a file called practice question for section 5.7. Okay? Because in the next lecture, our main focus will be on this file here. Okay? So there are some examples we are going to talk about in the next lecture.